Hi, we're Scarr and Chloe Young from EcoCircle International, and today I'm going to talk to you about the link between anthropogenic climate change and product production. So, what is anthropogenic climate change? Anthropogenic climate change is the increased rate of temperature change on our planet due to human-related greenhouse gas emissions. Both the causes and consequences of anthropogenic climate change are intersectional and international, ranging from climate refugees to zoonotic diseases. As you can see in this graph created by NASA, in 1950, Earth passed the CO2 levels to the highest point that it had had in the past 650,000 years. And unfortunately, we've not turned back.
Well, as George mentioned, there's something called anthropogenic climate change, which means that humans, or us, we're having an impact. So humans have an impact in a variety of ways, such as agriculture and emissions from other sources. And you can see this graph on the screen right now that goes over all of the different ways that humans impact the planet and climate change. But how do emitting these gases actually impact climate change and cause climate change? Well, this is caused by something called the greenhouse effect. The greenhouse effect is when greenhouse gases such as carbon dioxide and methane are trapped in the atmosphere, and then this traps heat, which makes the climate and the planet get warmer.
Now, we're going to focus on how the products in our life contribute to climate change. When we think of greenhouse gas emissions and climate change, people often think about the emissions that we're directly creating, such as the emissions that come out of a car when we drive it. But we don't often think about the life cycle of our products and the greenhouse gas emissions that occurred to getting that product to us. Manufacturing contributes to approximately 12% of global greenhouse gas emissions. In fact, 70% of a product's impact occurs before it even reaches us. In order to understand how to address the phrase reduce, reuse, recycle, we're going to give you an example. Let's talk about this bottle. A plastic bottle. Plastic bottles are often demonized due to marine pollution and actually what happens after it leaves the consumer's hand. But what really is the life cycle of a plastic water bottle and what happens before it reaches us?
So there's some newly published research, and this research says that the plastic industry accounts for 3.8% of global emissions, which is larger than the entire aviation sector. And if it were a country, the plastic kingdom would be the 5th highest emitter. And demand for plastics is actually set to rise, which means that all of these numbers are going to increase. At 380 million tons a year, we produce 190 times more plastic than we did in 1950. And if demand for this plastic just keeps on rising at the current rate of 4% per year, emissions from plastic are going to reach 15% by 2050.
The term plastics includes materials composed of various elements, such as carbon, hydrogen, oxygen, nitrogen, chlorine, and sulfur. Plastics typically have a high molecular weight, meaning each molecule can have thousands of atoms bonded together. Plastics, also called polymers, are produced by the conversion of natural products or by the synthesis from primary chemicals, generally coming from oil, natural gas, or coal, which we're going to talk about later. Most plastics are based on the carbon atom. Silicones, which are based on the silicon atom, are an exception. The carbon atom can link to other atoms with up to 4 chemical bonds. For plastics, the carbon atom can also connect to hydrogen, oxygen, nitrogen, chlorine, or sulfur. The group of atoms that are used to make unit cells are called monomers. When we combine monomers, we generate polymers, also known as plastic.
There are 2 main families of polymers: thermoplastics and thermoset plastics. A thermoplastic has connections of atoms that result in long chains, like a string of pearls. And at certain heats, they can melt and be molded into something completely new, and then they can solidify upon cooling. About 92% of the plastics in the world are thermoplastics. In a thermoset plastic, the carbon atoms form 2- and 3-dimensional networks instead of 1-dimensional chains. Thermoset plastics are characterized by not being meltable. Thermoset plastics such as unsaturated polyester boat hulls or the adhesives used to make plywood are created by mixing 2 specific chemicals and then immediately using the mixture before it sets up or cures.
Now let's talk about how this is is manufactured. More than 99% of plastics are manufactured from petrochemicals, most commonly from petroleum and natural gas. Plastic production is currently estimated to account for between 4 to 9% of global oil consumption. If trends in oil consumption and plastic production continue as expected, the consumption of oil by the entire plastic sector will account for 20% of the total consumption of oil by 2050. These raw materials, these fossil fuels, are refined to form ethylene, propylene, butene, and other basic plastic building blocks before being transported to manufacturers.
The production and transportation of these resins requires a lot of energy and therefore fuel, whereas NGL, natural gas liquids, which is the preferred input for ethylene production, is difficult to ship internationally. The next step involves turning these raw materials into Nurdles. For the polymerization step to work efficiently, the monomers must be very pure. All manufacturers purify raw materials and monomers, and then they capture the unused raw materials and byproducts for proper disposition. The hydrocarbons in oil and natural gas are heated in a process known as the cracking process. The goal is to break down the larger molecules into ethylene and propylene, which come from the crude oil refining process or other types of hydrocarbons. This is an energy-intensive process, specifically a thermal decomposition reaction, where greenhouse gas emissions include carbon dioxide and methane. Cracking typically occurs under pressure in the presence of a catalyst. All these monomers contain double bonds between carbon atoms. The raw materials have been changed into monomers and no longer contain the petroleum fractions. An example of polymer formed from addition polymerization is polyethylene, whose uses include grocery bags, packaging film, and wire insulation. Polyesters are made by condensation polymerization. Polyesters have many uses, including your clothing. In a 2017 study, polyester was found in approximately 60% of garments on retail shelves today, equating to approximately 21.3 million tons of polyester. This was approximately a 157% increase from 2000 to 2015.
It's estimated that 61% of this plastic water bottle's life cycle's greenhouse gas emissions is made during the production of plastic resin, which we just described, and transportation. These polymers are then molded and cooled into the shape of plastic resin pellets, also known as Nurdles. Now the Nurdles are transported. These plastic Nurdles are transported to different factories, emitting greenhouse gases. But let's pause this process quickly to talk about plastic Nurdles, because they are problematic. Plastic Nurdles are essentially pre-production building blocks for almost all plastic products. They look like tiny pellets of plastic about the size of a lentil. A 2018 study found that plastic pellets, also known as Nurdles, are estimated to be the second largest source of microplastics entering the aquatic environment in the EU, with an annual median emission of 41,000 tons.
Another assessment from the OSPAR Commission estimates that within the drainage basins of the OSPAR maritime area, plastic pellets are the fourth biggest source of land-based microplastics entering aquatic systems. This study estimates that between 2,600 and 26,000 tons of plastic pellets are released every single year. This equates to the weight of approximately 452 to 45,000 Asian elephants, which is more Asian elephants than there are currently in the wild today. Not only is this plastic pollution a big problem, especially because the small size of the Nurdles makes them super easy for animals to swallow, but this loss of Nurdles in the transport means that all of the greenhouse gases used to make them are just completely wasted. So we've been talking about the making of Nurdles, but how do we get from Nurdles into this? Well, there are a few different ways we can do it, but injection molding and blow molding are two of the most popular ways that are also cost-effective and produce high-quality plastic products. The main difference between the parts made by injection molding and parts made by blow molding is that injection molding creates solid parts, whereas blow molding creates hollow parts. Blow molding is the process of inflating a hot, hollow thermoplastic preform or a parison inside a closed mold, so its shape conforms to that of the mold cavity. Blow molded parts can be formed from a wide range of thermoplastic materials such as low-density polyethylene and high-density polyethylene. There are different ways that we can use blow molding, and they all make different items. The three are stretch blow molding, injection blow molding, and extrusion blow molding. Stretch blow molding is used mainly for carbonated beverage bottles, whereas injection molding and extrusion molding can make a plastic water bottle. In 2015, the emissions from manufacturing ethylene, which is the building block of polyethylene plastic, were 184.3 to 213 million metric tons of CO2 equivalent. And then this is equal to the amount of emissions of 45 million passenger vehicles for a whole year. By 2030, CO2 emissions from plastic production is expected to increase by 34% since 2015. Not only does this whole production process use extensive energy, it actually takes 3 times the amount of water in the plastic bottle to produce it. So in order to make this bottle, we use 3 times as much water that's in here.
So, now you're in the grocery store, and you want a plastic water bottle. You buy it.
You then take this plastic water bottle or whatever plastic product you bought to your house for consumption. Now at your house, you're thirsty, so you take a sip of water. But all of that effort that was put into making this, all those greenhouse gas emissions, all of the labor, all of the transportation, is just for a few sips.
So now it's thrown away, but out of sight, out of mind, right? Wrong. The remaining carbon footprint of this plastic water bottle occurs after the plastic is thrown away. The plastic is transported again to the waste management services. For the 10 to 20% of plastic bottles that do get recycled, in nowadays, they sort the bottles and melt them back down into pellets, the Nurdles we talked about. Although recycling is an energy-intensive process, it does save energy compared to creating new plastic. Every 1 ton, equivalent to 36,000 16-ounce plastic water bottles of recycled plastic, saves 5,704 kilowatt hours of energy, which is more energy than the average US residential utility customer uses in 6 months. It also saves 16.3 barrels of oil and 98 million BTUs of energy, as well as 30 cubic yards of landfill space.
However, this plastic will never be the same again. It's actually downcycled and its quality will decrease. Oftentimes, the plastic goes into making things like clothing or carpeting, and then the quality of these items will decrease over time, and the item will eventually end up in the landfill where it will sit for the next 500 plus years. Once it's at landfill, it goes through a process called incineration. Incineration releases all of the stored carbon in the plastic into the atmosphere again, as well as other air pollutants such as dioxins and mercury, and then these pollutants are toxic and damaging to human health. In 2015, the CIEL report stated that US emissions from plastic incineration were 5.9 million metric tons of CO2 equivalent, and this number is only increasing. These incineration facilities are disproportionately built near communities of color and low-income communities. As mentioned, burning waste can pollute the environment, so it puts the workers and the people in the neighborhoods at a much greater risk of diseases such as asthma. As plastics take centuries to degrade, disposal into landfills makes only a small contribution to the emissions in theory. However, as much as 40% of landfill waste is burnt in open skies, which dramatically speeds up the release of locked up carbon. Landfills have lower climate impacts than incineration, but once again, there are severe environmental justice issues with regards to the location of these landfills. In fact, the place we were at earlier, the manufacturing looking site, that was a place called General Iron, and they're currently being moved from a rich white neighborhood in Chicago to a much lower income neighborhood filled with people of color in the South Side. So clearly, we have a really big problem with plastics, but what's the solution to this? Well, I can tell you that it isn't just you or I making changes to our everyday lives, it isn't just governments imposing different legislation, and it isn't corporations just changing the way that they practice. It's all of us combined working together in order to create a solution that includes scientific factors, political factors, and social factors. A recent study notes that only by combining reduction in demand, top-notch recycling, decarbonization of energy, and large-scale adoption of bioplastics can we tackle plastic's contribution to the environmental crises. If we manage to do all of this, we can cut emissions from plastic by 93%. So now for the waste audit, what you're going to do is for the next week, you're going to keep track of everything you throw away. So next to your bin, you're going to keep some sort of piece of paper or way to keep track of what you throw away. And you can do this in whatever method you like. You could do a list, a tally, a table, or anything else.
Once you're done with this video, go to the guide sheet to see how to appropriately set up your experiment. Now on to the method.
So it's the end of the week, and it's time to consolidate all of our data and figure out how many greenhouse gases our waste from this week emitted. So we're going to count up everything and then go to the greenhouse gas emission calculation table that was included in the guide sheet.
So now, using the greenhouse gas emissions calculation table, multiply how many times you use that object by the greenhouse gas emissions of that object's production. Now, add them all up, and that is the greenhouse gas emissions as a result of your waste. If the object is not in the table, compare it to the most similar object or do additional research of your own to find out how much greenhouse gas emissions was emitted as a result of that product's production.
So once you've calculated all of your numbers, it's time to reflect. In the guide sheet, you can find a list of reflection questions that can help guide this process. So after our waste audit, we reflected on the plastic water bottle that we've talked about quite a few times today. We realized that we did not need this plastic water bottle in the first place. We could have refused it. Instead, we could have used a reusable bottle like this one.
After those reflection questions, repeat your week-long waste audit. So now you will be able to compare week 1 and how much greenhouse gas emissions of your results of a waste of that week and week 2. Also, you gotta consider the extraneous variables. Is there anything besides your knowledge based on the past week of the waste audit that will impact your results? For example, is a family member out of town that week? That could definitely reduce your family's waste. Thank you so much for your time and your dedication for using science to help our planet.
If you want to contact us to ask us any questions, give us any feedback, or just share your results from the waste audit, please visit the website of our nonprofit, ecocircleinternational.org, and use the contact form there. Bye!